In 1875, Josiah Willard Gibbs published an enormous volume explaining how chemical reactions and phase transitions could all be deduced from the first and second laws of thermodynamics. Now, the study of chemistry is vast. It could almost be its own subject. But here today, our goal is just going to be to understand how chemical reactions can be understood in terms of the thermodynamic laws that we've been developing so far. We're trying to answer the question of what is a chemical reaction and why does a chemical reaction happen? Does it go forwards? Does it go backwards? Is there some happy medium where it won't happen at all? These are questions that surprisingly we can answer with the laws of thermodynamics in terms of thermodynamic potentials. First, let's describe the notation that we're going to use for a chemical reaction. In general, we have some number of reactants that merge together, collide with each other. Some microscopic process happens where they change their arrangement of atoms within the molecules and make products. We'll generalize this to saying that there are two reactants, A and B, and two products, molecules C and D. Now, every reaction doesn't have two on the left and two on the right, but we can use what we get here to generalize to 1, 3, 4, any number. It will be clear how to make those modifications. So in every reaction, there is a certain number of molecules A, B that go in, and a certain number of molecules C and D that come out. And the reaction must be balanced, since in chemistry we cannot destroy or create any new atoms. We introduce what are called stoichiometric coefficients. We'll symbolize these by x variables with subscripts for the chemical compound. When a reaction occurs, the number of A's, B's, C's, and D's changes, and it changes in a specific way based on the stoichiometric coefficients. Since the arrow is drawn in this direction, the number of products will decrease. So the amount of moles of chemical A will decrease based on its stoichiometric coefficient and the number of reactions that occur. Dn we will use to symbolize the number of reactions measured in moles. The number of molecule B, C, and D will change in a similar way. The number of reactants decreases if reactions occur in the direction of the arrow, and the number of products increases. Notice that this doesn't say anything about how many of these molecules there were to begin with, just how their numbers will change if there is a reaction taking place. Now, these formulas here relate the change in each type of molecule to the number of reactions that occur. So there's a large number of, say, conservation quantities in a chemical reaction. For example, if we formed the quantity XC times Na plus XA times NC, this quantity would remain constant. Why would that remain constant? Well, if I take the differential of it, DNA is minus XA dN, and the differential DNC is plus XC dN. So the change in this quantity is exactly zero. And you can construct any number of these constant quantities, a whole bunch of them, based on different combinations of the number of each species. Now, some of those are interesting. They might end up being equal to the number of atoms of a specific type. And some other ones are just sort of not interesting. Now, every chemical reaction has to have specific values for its stoichiometric coefficients in order to be balanced. A balanced reaction is one where we have equal numbers of atoms of each kind on each side, and equal number of electrons. If reaction involves electric charges or ionized molecules. It's best to do an example to see how this works out. Since we're doing this in general, I'm going to make up a reaction. I've never heard of this reaction. I don't know what name it is, but I know that it can be balanced. Let's say we have water, and we attempt to react that with, sulfur dioxide. Now, there are many products that this reaction could make, but in our studies here, we're going to always assume a certain reaction could be possible and then analyze its properties. So I'm beginning with this made-up reaction. I have no idea if it even works. We'll find out eventually. We add water to sulfur dioxide, and that creates hydrogen sulfide and oxygen gas. Now, this reaction is unbalanced at the moment. If we count up, there's 1 oxygen here, 2 here. So there's 3 total on the left, but only 2 total on the right. And other atoms, H and S, are also possibly not balanced. Now, there may be some shortcuts for balancing these that you've heard about in chemistry courses, but I want to show you a general method of balancing any chemical reaction that will always work and is methodical. Okay, so it's in terms of the stoichiometric coefficients. If we imagine that there is a coefficient A in front of, coefficient XA in front of the water, a coefficient XB in front of the SO2, a coefficient XC in front of the H2S, and a coefficient XD in front of the O2, then we can evaluate the condition that equal numbers of atoms have to be on each side. We can turn that into equations. So for example, if we look at the hydrogen content of each molecule, on the left we have 2XA coming from the water, we have none from this, and on the right we have 2XC coming from the hydrogen sulfide and none from this. So therefore we conclude that XC must be equal to XA when the equation is balanced. If we look at the oxygen, let's look at the sulfur. We have 1 times XB for the SO2, and we have 1 sulfur in the XC for the H2S and none for the rest. So we conclude that when the equation is balanced, XB must be equal to XC as well, and because of the previous one, it must also be equal to XA. Finally, we'll look at the oxygen. We've got XA from the water, we've got 2XB from the SO2, we have none here, and then we have 2XD from the oxygen O2 gas. So this equation tells us then that XA and XB, XA plus 2XB must be 2XD. XA and XB we already concluded were equal, so this is going to be equivalent to saying that 3XA must be equal to 2XD when the equation is balanced. So there's infinitely many solutions to this, but in chemistry we generally try to keep our X values as small integers, not fractions, not really large numbers. So I'm going to choose one possible solution, which is to make XD equal to 3, XA equal to 2. That solves this equation, and then therefore XC will be equal to XA, which is 2, and XB will also be equal to XA, which is 2. So the balanced reaction will then have a 2 here, a 2 here for XB, a 2 here for XC, and a 3 in front of the O2. And you can check that that's balanced. Right? So this is a good method if you've got a complex equation with lots of things, you can turn them into algebraic equations. If we had any ionization charges on here, like the superscripts plus or minus, plus 2, minus 2, those things, ionization, or if we had any electrons, E minus counts for a -1 charge. That would give us another quantity which had to be equal on both sides. All right. Now that we have a balanced reaction, let's step back and think. Try to answer the question, will this reaction happen? How could we decide? Well, in general, whether a reaction happens or not is not something that has a once and for all answer, right? We know that if we had, say, if we wanted to run this reaction but we didn't actually have any SO2 in our system at all, then it couldn't go forward because you can't have a negative amount of particles. But if you had a lot of SO2, then it could. So the way a reaction, whether a reaction goes or not, might depend somewhat on how much of these things there are. Or it could also depend on the external ambient pressure or the external ambient temperature. So we'll answer this question, why does a reaction happen, the same way that Mr. Gibbs did. A reaction happens because nature seeks equilibrium. And we know that nature seeking equilibrium results in maximizing the entropy of the universe. There it is. We've got to maximize the entropy of the universe. Now, if we perform our chemical reaction at constant pressure and constant temperature, which is normally done in a chemical lab, we know that maximizing the entropy of the universe is equivalent to minimizing the Gibbs free energy. So let's just write that down quickly. Seeking equilibrium is equivalent to saying that if we maintain a constant temperature and pressure, nature will spontaneously execute processes that minimize the Gibbs free energy. If we maintain a constant temperature, but perform our reaction in a sealed vessel, so it has constant volume, then we know that nature will spontaneously do processes that minimize the Helmholtz free energy. And the last case that we really see in experiments is called a, well, we have a sealed container that is insulated from the outside. So this is actually called, I think, a bomb calorimeter, because if you open it up, it might blow up because you got it sealed and you got it insulated so it can't cool off and it can't expand. So it can be dangerous. But in this situation, we know from the second law we want to maximize our entropy, S. So what does it mean to minimize G, minimize F, or minimize S? Let's take a look at what we could do to change the Gibbs energy in this first line. dG, remember the fundamental identity is equal to minus S dt plus V dP. And then since we have multiple chemical substances, multiple different molecules, we have one additional term of chemical potential for each one. So we have mu J dnj, which is summed over all the J species in the situation. So here J would be 1, 2, 3, 4, or A, B, C, D, and I'd have 4 terms for chemical potential here. So if we're holding temperature and pressure constant, then these two terms are going to be 0. And the change in the Gibbs free energy will entirely depend on the chemical potentials of the species and whether their mole numbers change or not. What about the second line, Helmholtz? In general, to change the Helmholtz for energy, we have minus S dt minus P dV plus mu dN. And in this situation, temperature is held constant, volume is held constant. So again, minimizing F will depend only on whether this chemical term is positive or negative. Lastly, if we look at the bomb calorimeter, it's a little more complicated, but remember that entropy can be written as a function of energy volume and particle numbers. So that is a expansion for ds. Now, if the total energy is held constant, this term is gone. If the volume is held constant, this term is gone. And so again, we get this term here, which only depends on the number of moles changing. Remember that ds dnj was equal to negative mu j over T. Okay, so even though we don't hold temperature constant in this bomb calorimeter, the temperature is the same for every different molecule inside the chamber. So again, we get something where this is minus 1 over T times the sum of mu j dnj. So again, this mu times dnj term is basically the only thing that determines whether we're going to get closer to equilibrium or not. Notice here that the same term appears in each part. So minimizing G is dependent on this, minimizing F is dependent on this, and maximizing S is dependent on the opposite of this. So this quantity here, the sum over all species of its chemical potential times how the mole number is changing, is a crucial quantity for determining if a chemical reaction is going to happen or not. So we call this, in sort of a perverse notation, this is called the delta G of the reaction. All right, the delta G of the reaction. Now, it's not really a delta G in terms of like I changed the temperature and pressure and got a different Gibbs energy. It's a delta G in terms of performing the reaction. So this quantity is the determinant of whether the reaction happens or not. So remember, delta G was equal to the so since this is not called delta G yet, this is dG. So that's dG still. Okay. All right, so this dG quantity is the change in the Gibbs free energy due to a change in the mole numbers. But when we do a chemical reaction, the mole numbers for each species, they don't change in an arbitrary way. This is true for any arbitrary change in dN. You know, conservation laws just ignored. But in a chemical reaction, remember we just wrote that each substance has to change according to its stoichiometric coefficients. So stoichiometric coefficient there, plus sign for products, minus sign for reactants. So in here we get a plus or minus with the stoichiometric coefficient, and each term in the sum is multiplied by dn. So if we move this dn to the other side, remember dn represents the number of reactions that occur. We get something that depends only on the chemical potentials and the stoichiometric coefficients of the reaction. Again, plus for products, minus for reactants. Now, nature wants to minimize the Gibbs free energy. And so if this quantity here is positive, all right, so this quantity here is what we call delta G. As again, you can see, it's not really a change in G, it's a derivative of G. But this, unfortunately, with the historical notation, this is called the delta G of that reaction. And if the delta G value is positive, then performing one reaction increases the Gibbs free energy, right? This is the dGdn. So if this side is positive, then doing one reaction means G goes up. So if delta G is positive, then the reaction must have a negative dN to decrease the Gibbs free energy. So if delta G is positive, the reaction goes in reverse. If delta G is negative, the reaction goes forward. And if somehow by coincidence or by setup, the delta G value is exactly 0, then we are at equilibrium. So it's this quantity here, the delta G of the reaction, which determines whether the reaction will happen the way we said, will happen backwards of how we said, or will not really happen at all. Now remember that in general, these chemical potentials can depend on things like the pressure, the temperature, and they can also depend on the relative fraction of these different components. So as the reactions proceed, generally the chemical potentials change. So this approach to equilibrium is highly non-trivial, right? You do a reaction, the mu's change, you get a different delta G. Does it still go forward, or does it reach equilibrium? So our goal, mainly in deciding whether a reaction occurs or not, is going to depend on figuring out these chemical potential values, getting the delta G. Now when we find the delta G, we can tell whether the reaction is favorable in terms of the second law, but it still doesn't tell us anything about really how fast that reaction proceeds. In general, a larger delta G value means that the reaction will be more violent, faster, more likely to happen, but not always. It just tells us which way the reaction has to go to get to global equilibrium. So if we want to form this quantity, we need to look at the chemical potentials that come from each type of substance. So we'll go through 4 different types of substances and show how their chemical potentials can be calculated or looked up in a table. So the first case, which we can easily write down, is an ideal gas. An ideal gas doesn't interact at all with anything else. So for its chemical potential, say we have an ideal gas as our jth component in the system, we can just use the chemical potential of that gas by itself. And going back to earlier material to look this up, remember what we would get would be something like negative RT times the log of V over N times 4 pi m KT over H squared, 3/2. Okay, so that was the formula for a monoatomic ideal gas. And that's quite messy. We don't really want to have to look up the mass and Planck's constant every time we have gas in our substance. And also, just a little dirty secret is that this formula doesn't actually agree with the units or scale that chemistry tables use to calculate chemical potential. So if you look in the table and calculate mu based off of this, it won't be the same. There's a good reason for that we'll see later. But we're going to arrange this in a certain form now that's going to make it easier to calculate for any type of ideal gas, not necessarily just monoatomic. Notice that we have a volume over particle number here, so we can change that basically into one more factor of temperature on the top and one factor of pressure on the bottom. So in general, then we write this as the pressure of that component of the gas the temperature of the system as a whole, F over 2 power from this, F is the degrees of freedom, and a plus 1 power from the ideal gas law with V. So we get this, and of course we can't just like ignore all those units in there and get the same thing. So there's a standard value in the front that comes from putting all these pressures and temperatures equal to the standard pressure and standard temperature. Right, so we can write it like this. Also, we can just use the properties of logs to change this around inside the logarithm in exchange for a plus sign there. So let's point out a couple of things here. The mu J0 here, this is called the Gibbs free energy of formation, and this is the value that we would need a table to look up. There are various type of chemistry experiments that can determine this value, and luckily they've all been written down in a large table for us. But that's just some constant energy value that we will look up for each different type of gas molecule. So this in principle, this includes all the M's, the H bars, and if it's diatomic, the internal spring constant, and all that crap that goes into this reference chemical potential. Then inside of the logarithm, this Pj, this is not just the pressure of the whole system. Since we're only talking about one of the components here, this is the partial pressure of component J. So if your reaction involves a mixture of gases, then the Pj is different for each gas and independent based on how many there are. So the total pressure is the sum of all the partial pressures over all the components that are gases. And each partial pressure obeys the ideal gas law on its own. So number of moles times RT over the total volume of the sample chamber. All right, so there's a formula there. Then we've got the formula for the chemical potential of the ideal gas. And this is the one we would want to use if we did a reaction at a known pressure and a known temperature. Now, since we're not going to do the entirety of chemical thermodynamics here, just an introduction to it basically, we're usually going to consider reactions that occur at standard temperature. Right? The dependence on temperature here is a little bit more involved than the dependence on pressure, and so that makes things harder mathematically when we get to the end and try to solve. Okay, so that's how we handle ideal gases. We will look up mu J zeros in a table. Here is the table. It's been posted on Sakai. So the chemical compound is on the left. The state of matter is the second column, and if it's got a G there, then that's a gas, and that's where we would pull this value from. The value we're talking about here, Gibbs free energy of formation, mu J0 is the R right column. All right, the second type of system or chemical state that we will encounter quite frequently is a dilute solution. Okay, so the chemical potential formula for the dilute solution is worked out in the textbook. There's a whole model for dilute solutions. And I won't repeat that here, we'll just say the results. So the chemical potential here with the subscript A is for the solvent. And that's usually not what we're interested in a chemical reaction. We're interested in the things that are dissolved, which are the solutes. So the chemical potential of solute in a dilute solution also has this reference chemical potential here. This is the Gibbs free energy of formation for that chemical compound. It depends on the temperature, the ideal gas constant, and the logarithm here is of a quantity called the molality, MB. And that's directly related to the number of atoms, molecules of type B in the dilute solution. So it's moles of B divided by the number of kilograms of the solvent. So we usually just put this MB in here and realize that that's then going to be measured on a scale of moles per kilogram. So if MB had a value of 1, there will be 1 mole of particle B versus 1 kilogram of solvent. The reactions don't change the amount of solvent in a meaningful way usually, so we can just take our MBs to be proportional to the number of moles in the system. If molecules are created as products of reaction, then the molality will go up. Okay, so there's our formula for chemical potential of a substance B in a dilute solution. All right, the third and fourth type of chemical state that we will find out the chemical potential for is solids and pure liquids. So a pure liquid is not something dissolved in water, but a pure thing like a bromine or mercury or a melted oil or something like that. A pure 100% of a certain chemical compound in a liquid state. So the thing about solids and liquids is that they mostly have a constant volume and they mostly have a constant entropy content. Of course, these change a little bit as you compress them or heat them up. But for the scale of the reactions, those terms are not very important. The chemical potentials of these things are mostly constant. So if we have a solid or a pure liquid in our reaction, we can simply look up the value in the table for the Gibbs free energy of formation and treat the chemical potential for that substance as a constant, independent of temperature, independent of pressure. That's usually what we'll do. Now, I do want to make you aware that if you go to approach a reaction that occurs at an extreme temperature or an extreme pressure, different from standard conditions, that this approximation is not valid. In small deviations, in temperature, this chemical potential vary depending on the entropy of that substance. And for small variations in pressure, there is an increase in the chemical potential proportional to the molar volume of that substance. So molar volume is volume per mole of atoms. And this is something that we just get from the Gibbs-Duhem relations, right? d mu dt equals minus s, and d mu dp equals positive v. So if we have a large variation in temperature where we need to include that change in the chemical potential, we can add these on. But generally we're okay. We're either at standard temperature and this turns to 0, or we're at standard pressure and this turns to 0, and we just get a constant value for this chemical potential. Either way, the chemical potentials of solids and pure liquids vary much less as the reaction occurs than do the ones for dilute solutions and gases. Now we have all the ingredients that we need to look at a given reaction and really predict whether it's going to happen forward, happen in reverse, or not really happen at all. So the rules are, we write down the reaction, we balance it, so first write the reaction. Secondly, we have to balance the reaction. Third, we have to write down expressions or calculate the mu's for each chemical compound that's in the reaction. And when we get all those, we can calculate the delta G. So the delta G depends on the stoichiometric coefficients and the chemical potentials added all together. Then based on the delta G, if it's negative, the reaction goes forward. If it's positive, the reaction goes in reverse. And if it's zero, it will be at equilibrium. So let's do an example where we see how this works. And we'll do it for the equation that I made up at the start. We'll come over here and have our H2O plus SO2 turning into H2S plus O2. So that's the reaction. Then we balance it. So we had a 2 here. We had a 2 there. We had a 2 here. And a 3 in front of the O2. Okay, so this is our XA, our XB, our XC, and our XD. Third step, we have to write down an expression for the chemical potential of each of these components. Now, I do have some freedom here at this point to decide whether these components are going to be maybe in the liquid state, in a gas state, or in an aqueous solution or a solid, right? I get that choice. For this example, we will treat all of these as if they're all in the gas state. That doesn't have to be done this way, but it has a certain simplicity to it because everything depends then on pressure. So if we put these as subscript G in parentheses, that indicates that they're all to be considered in the gas phase. And then our chemical potential for each one will be given by the formula for the gas. Okay, so this is the point where we then need to go to the table. So first chemical compound there is H2O in the gas phase. So flip through the table. The table is alphabetically by compound. So H2O appears on page 43. I'm using the gas state here, and the Gibbs free energy there is minus 228.59 kilojoules per mole. So that's the reference value that it would have at standard temperature and standard pressure. I'm going to allow the pressures of this substance to be different. Having every single gaseous component at 1 atmosphere of partial pressure is a little bit artificial. It's reasonable that they're all at the same temperature, but having them all at the same pressure is kind of artificial. So I'm going to allow them to have different partial pressures. So there's mu A for the water vapor. For the rest of these, I also have to go to the table and look them up. And I've already done that, so I'll just write them down. Now, an interesting point here for oxygen, the table lists its reference chemical potential energy as actually 0. And this goes back to what I mentioned earlier about how the formula for the chemical potential of an ideal gas, when it's monatomic, wouldn't actually match up with the values in the table. And this is because when chemists started recording these values for given reactions, there's a certain arbitrary freedom that you have to set a reference level for each different atom. Because the atoms are conserved on each side of the equation, any offsets to the Gibbs energy of that atom will cancel out when it's all added up, right? So if I say added 10 kilojoules per mole to every oxygen, well, I have an extra, I've had an extra 2 there, an extra 4 there, but then I'd have an extra 6 on this other side, so it would cancel out. So there's a freedom there, and to make most use of that freedom to reduce our workload, we've set the most stable state of any chemical compound, of any atom in its most stable chemical compound, we set the Gibbs energy of formation to 0. So we're allowed to do that, and that means the O's, since O2 is the most stable state of oxygen, that has a 0 there. So when something has another value here, you can tell that it's probably not the most stable state of those atoms. Okay, now we've got all the chemical potentials. We will have to put them into a big whopping sum to get our expression for delta G. So now this expression is going to involve everything we've got so far. We have to think about whether that is a product or reactant, what its coefficient is, and its formula for mu. So I'm going to have 4 terms here. The first one will come from the H2O. It's a reactant, so it's going to get a minus sign. Its stoichiometric coefficient was a 2, so there's a minus 2 multiplying this whole chemical expression here, minus 228.59 plus RT log P A. That whole thing is multiplied by negative 2. And then onto that we add another minus 2 for the sulfur dioxide. Then for the hydrogen sulfide, the H2S, we have a product, so it gets a plus. It gets another factor of 2 there because that's its coefficient. And then we have the minus 33.05. And the RT. And then for oxygen, we have a plus 3. RT log PD. Okay, so that's our formula for delta G. And after we write that all together, there's a standard way of simplifying this. Notice that we get a lot of quantities that are just constants, right? The minus 2 times the minus 228, all these things in front, those all just amount to some overall constant. And then we have a bunch of things that are multiplied by RT and have a logarithm. So we can group these up in a certain way. If I do this, I'll get 991.46 for all the constant terms. And then for the terms with the RT and the logarithm, what we do is we leave the RT in front. We take this factor of 2 here, and we use the rule of logarithm to put it into the power of the inside argument. So we would have a PA to the minus 2 power. So PA to the squared on the bottom. From the second line, we get a PB squared on the bottom because it's a minus 2. From the third line, we get a PC squared on the top. And from the fourth line, we get a PD cubed on the top. And these pressures are all measured relative to standard pressure. So it doesn't matter that they don't line up in terms of units. A pressure value of 1 here would equal 1 atmosphere, or 1 bar, actually. Okay, so this is our formula for delta G in its most concise form with arbitrary partial pressures. And as you can see here, the first term here is positive and quite large relative to the scale of individual Gibbs energies. So the second term here is going to have to be pretty small to make this thing balance up to zero. So this is a reaction where we can say with pretty strong conclusion that this reaction is going to strongly want to go in reverse, right? The products have a much higher Gibbs energy than the reactants. Nor at any normal pressures, this term is going to be, of order 1 or something. And so this reaction is going to go strongly in reverse. Let's remind ourselves what it was. It was water and SO2. We assumed that it might react to form hydrogen sulfide and oxygen. That's not the balanced version. Our conclusion here is that while this hydrogen sulfide would really just love to eat up the oxygen and make a bunch of water and sulfur dioxide. And if we remember any sort of rules from chemistry, hydrogen sulfide is kind of a, it's not the best thing to have around. It's kind of a reactant, kind of corrosive, kind of poisonous if you breathe it. So those sort of things, the reason that they're like that is because they have a high Gibbs energy formation, and they don't want to exist. They want to turn into other things. So oxygen is the same way. That's why it's a good thing to breathe in. It has a lot of potential to react and to release some energy. So these two things love to get together and break down. And so this reaction goes in reverse. Okay. Now there is a lingering question about these pressures over here. Is it possible to choose some pressure values that could make this reaction stop? And because this is inside of a logarithm here, we know that a logarithm is it's an entire function, right? It has a vertical asymptote at an argument of 0. It goes to negative infinity. And as the argument goes out to positive infinity, the logarithm continues to go and grow. It doesn't have any limits to its range. So there's always some combination of pressures which could balance out this 991 and make the delta G 0. And that would be the equilibrium condition for this reaction. If you go through the calculation, which I will leave in the notes but not do on the board here, if we go through the calculation, what we will find out, kind of fits with our qualitative answer. What we'll find out is that to balance this out, this logarithm, must be very, very small, like on the order of negative 500. And to get a negative 500 after taking a logarithm, the things inside have to be something like e to the minus 500 power, right? E to the minus 500 power. So the terms inside of here are going to be extremely close to 0. And that means the denominator must be much, much larger than the numerator. Denominator came from A and B. Numerator came from C and D. So species C and D, they have to be almost gone to make this equation balance. If we do the calculation, we'll find out that it's the kind of reaction where we would actually say that it eats up basically every atom it can, because the equilibrium value of pressure C and pressure D is on the order of something like, I've got it here, 10 to the minus 53 pascals for the pressure of component D, if we adopt some initial condition and let it go. So if something is at 10 to the minus 50 pascals, it's got 10 to the about 10 to the minus 50 moles, and so about 10 to the minus 30 atoms, and 10 to the minus 30th atoms is such a tiny fraction of an atom that there's probably not even one atom left. So this reaction goes essentially all the way, and there would be no products left. It would form all the reactants. The reaction goes in reverse. Okay, so this sort of gives us an exhibition of why chemists are so preoccupied with rules and naming and categorizing different compounds. Because if we choose a random chemical reaction like this, and we do the math from the tables, we could easily get a result that says, this reaction, it almost never even has to happen, because any H2S you get at all is just going to, boom, it's going to go this way. And so you might look at this and say, well, obviously this is an oxidizer and this is an acid or something. So yeah, it's going to go and react together. And it's good to have those rules of thumb handy where you can just glance at the compounds, know what they're basically going to do, what reactions are absurd, and what reactions are almost guaranteed. But the thing that underlies that, which we have deduced today, is the Gibbs free energy. If you encounter a reaction that your rules don't explain, or you want to be precise, you can always go back to this table of Gibbs energies of formation and find out precisely what it takes for that reaction to happen.